This is chapter 9 for AP Chem Review on chemical bonding. There are two chapters in this. This is chapter number 1. First thing it talks about is what is an ionic and a covalent bond. An ionic bond, they state, is the electrostatic force that holds ions together, so your positive and negative forces hold each other together. I'm going to give you a couple examples Lewis dot-wise. One's going to be of lithium chloride, one's going to be of magnesium nitride. So we go over to the board here, how I'd start off with lithium has 1 outer electron. Chlorine has 7 outer electrons. What happens in an ionic bond is the metal gives its electron to the non-metal. So lithium is going to give its electron to chlorine right there. Now chlorine's at the octet, lithium's going to be like helium. My final answer for the Lewis dot for that would be lithium with a plus. Chlorine will have 8 electrons around it and be a minus. The second example I gave you was magnesium nitride, which first off, know the formula of these things. Magnesium nitride is Mg3N2, which means I have 3 magnesiums and 2 nitrogens. I'm just going to show you what one of each would look like. Magnesium would have 2 electrons. Nitrogen would have 5. What's basically going to happen is all the magnesiums are going to give their electrons to the nitrogen. There's 2 ways you could write your final answer for this. One, kind of a shorthand version, is say I have 3 Mgs, which are a +2, and I have 2 Ns, which are a -3, or you could draw out 3 magnesium +2s and 2 nitrogen -3s. Either version works. Again, you'll see a lot of textbooks show this though. Oftentimes they'll also put the ion in brackets to show here's the thing, there's 2 of them, here's the thing, there's 3 of them there. So there's 2 ways you can do ionic. This is one where showing the coefficient and the atom itself, or you could just draw all of them out. Whichever you prefer doing should be fine. The next thing to talk about is covalent bonds. First thing to mention with covalent bond is the bond in which 2 electrons are shared by 2 atoms. I'm going to give you a Lewis dot of a few examples here, starting off with water, which water I mentioned has lone pairs to it. Water's formula is H2O. So if I have hydrogen, oxygen, and hydrogen, what happens is they share electrons, they share electrons. My final drawing, and I'm going to draw it in the correct geometry, something we'll talk about in the next chapter, would be in this format here. Again, a bond represents 2 electrons, 1 from each atom. Here's a pair of electrons, here's a pair of electrons. The next sample that you'll see is called nitrogen. Nitrogen is N2. N2, nitrogen starts with 5 electrons, it's going to share 3 times. This forms what's called a triple bond. Nitrogen is triple bonded to itself, so we can have more than single bonds if we wanted to. The next example is ethylene, which those of you who do not know ethylene, again, when we get to the organic chemistry unit, you'll know what that is. It is C2H4. Typically, carbon wants to bond 4 times. Hydrogen only wants to bond once because it's referred to as a terminal atom. It ends molecules. The final answer for this one is going to end up being carbon with a double bond to itself, and then single bonds to the hydrogens. The last thing to mention here, I mentioned bond length. Single bonds are usually longer than double bonds are longer than triple bonds. So there's a strength involved with bonds, which once again we'll talk about at some point, but then there's also a length associated with these bonds that you need to be aware of. So a simple multiple choice would be which bond length is longer. If we move past Lewis dot, the next thing we need to be aware of is what's referred to as electronegativity. This is a trend of the periodic table that we didn't cover in the trends unit because it deals specifically with bonding. Electronegativity is referred to as the ability of an atom to attract towards itself electrons in a chemical bond. This is what makes up polar and nonpolar covalent bonds. So what you could do is you could subtract the electronegativity values of the 2 atoms to determine is it polar or nonpolar. A quick way that we usually tell you to check and see if that's right is if the 2 atoms are right next to each other in the periodic table, they probably have a similar polarity, or a similar electronegativity rather, which is going to make it a nonpolar bond. If there's at least one element between the 2 atoms that are bonded, then there's going to be a large enough difference in electronegativity to make it a polar bond. By the way, if you want to know the trend for electronegativity, which we talked about trends in the last chapter, as you go down the periodic table, electronegativity decreases. As you go left to right across the periodic table, electronegativity increases. Fluorine is the most electronegative atom that we have. So even though the trend is left to right increase, that stops before we get to the noble gases, because noble gases do not want to pull or gain on electrons. Next thing to mention is that oxidation numbers are determined by the electronegativity. This is an important thing to remember when we are dealing with Lewis dots coming up in things called formal charges, that the oxidation numbers of the atoms can be determined by the electronegativity. Next slide is on what formal charge is. Formal charge is referred to as the difference between the valence electrons in an isolated atom and the number of electrons assigned to that in its Lewis dot structure. A good example is going to be ozone. So I'm going to draw ozone on the board. Ozone, first off, is O3. Now, normally oxygen would want to bond twice, but if it's oxygen, 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 it can't have only two bonds to get to the octet. So what happens is something fairly unusual. If I draw out the Lewis dot for each oxygen, these two pairs will share right away. Now after that, this is at 7 electrons, this is at 8, this is at 7. Everything needs to get at the octet. So what ends up happening is something kind of unusual. This will share with this atom and then give its electron here. Your final answer for ozone would have something that looks like this. How this deals with formal charge is oxygen started with 6 electrons directly around it. Now it has 1, 2, 3, 4, 5, 6, 7. It gained an electron. It's a -1 formal charge. This oxygen over here has 1, 2, 3, 4, 5 electrons around it. It lost an electron. I'm kind of showing that in my mechanism up above. It's a +1 oxidation number. And again, on the final one, 1, 2, 3, 4, 5, 6, that one works out just fine, so there's no problem with that one. I'm going to give you one more example, which is dinitrogen oxide. Dinitrogen oxide is N2O, and there's 3 ways N2O can be formed. It could be double bonded both ways. It could be nitrogen triple bond to nitrogen, single bond to oxygen, or flip the triple bond around. These are the 3 possibilities for dinitrogen oxide, but only one is the best representation, and this is where formal charge will tell us which one is the best. If I split the bonds, this nitrogen here is 1, 2, 3, 4, 5, 6 electrons. That's a -1 formal charge. This nitrogen here has 4 electrons. It must have lost one. That's a +1 formal charge. Oxygen's at a 0. The second version here, I draw my 2 electrons there. Nitrogen here is 1, 2, 3, 4, 5. That's just like it should be. Nitrogen right here, lost an electron. It's a +1 formal charge. Oxygen has 1, 2, 3, 4, 5, 6, 7. It gained an electron. Last version. Nitrogen here has 1, 2, 3, 4, 5, 6, 7. It gained 2 electrons. This nitrogen lost 1. This oxygen lost 1. Basically, the rules of formal charge are trying to say that when you draw a Lewis dot, you don't want to deviate from what you started at. So when I look at this bottom example here, nitrogen isn't just going to gain 2 electrons. This is deviating further 2 than the other ones are only deviating by 1. This cannot be the correct answer. So now I have 2 possibilities, either a -1 +1 here or a -1 +1 here. The rules of formal charge say the more electronegative atom is the one that's going to want to gain that electron, which means this is more electronegative than nitrogen. This is the correct answer for what dinitrogen oxide would look like, because this is the most likely possibility. Lower formal charges, negative formal charges on the more electronegative atom. If we move on to the next slide, it's going to be referring to what are called resonance structures. Resonance structures are one way of representing a molecule, is not the accurate representation overall. We're actually going to go back to the ozone example I gave you a second ago. So if I redraw ozone up here, ozone is O3, which once again is a double bond and a single bond. Now ozone could flip the double bond to the other side, so it could just as easily be this. When you see an atom being drawn more than one way and both ways are basically the same, what that tells you is it's a resonance structure. And technically, neither of these are correct. Actually, what's happening, ozone is a blending of these two. In Lewis dot, we know how to draw single bonds, we know how to draw double bonds. It turns out that the bond length between these two and these two are exactly the same. So it's not really a single and a double bond, it's more like a 1.5 bond for each of them. But Lewis dot can't have you draw that. So it's one of the limitations of Lewis dot. When you see resonance structures, realize it's more of a blending of these different things. I'm going to give you a couple more examples as well. One would be the carbonate polyatomic ion. Carbonate polyatomic ion is CO3 with a -2. And I'm only going to draw one version for you here. This is one version of the carbonate polyatomic ion with a double bond to one oxygen, a single and a single. And this would be a -2 overall because here's a formal charge of -1, here's a formal charge of -1. Technically, I could draw the double bond here instead in 2 singles, or here instead in 2 singles. So it's a resonance structure. Benzene's the last one. Benzene is a 6-sided ring. And I'm going to do the shorthand version of it. This is the shorthand version of it, which again you learned in organic chemistry, where I could draw it here with double bonds in this spot, or I can draw the double bonds in the opposite spot. So once again, it's really a blending of the two. Whenever you see this kind of double arrow to show more than one possibility, that's what it's referring to. Next thing we're going to go over is exceptions to the octet rule. So there's a few of them. The first one's called an incomplete octet. An incomplete octet means you have less electrons than 8. But sometimes there's no avoiding that. 2 examples that we talked about in class are beryllium hydride or boron trifluoride. So on beryllium hydride, beryllium only has 2 electrons. So it can bond to each hydrogen, but that's all it can do. So it can't get to the octet because it doesn't have enough electrons. This is still a stable molecule for it. Same thing can be said for boron trifluoride. Boron trifluoride is just this. Now some might say, well, why not make a double bond, take these 2 electrons and put it there? The rules of formal charge will not let you do that though, because then you'd have a positive formal charge in fluorine, which cannot occur. Second exception to the octet rule is odd number molecules, which are called radicals or free radicals. The Lewis dot for nitrogen dioxide, which is NO2, would look something like this. This would be the Lewis dot for nitrogen dioxide. Notice that there is 1 lone electron. There's an odd number of electrons in this problem. 6 and 6 and 5 gives me 17 total electrons. Everything can't get to the octet if you have an odd number. So those free radicals, very reactive because they want to pair up that electron, which is why I always stressed it's important to draw your Lewis dot to have pairs of electrons, either bonded pairs or unbonded pairs. But you don't have individuals because that's what free radicals represent. The last exception to the octet is what we refer to as the expanded octet. So you can go above 8 total electrons. In the next chapter, we'll talk about different hybridization that proves that, like sp3d and things of that nature. Sulfur dioxide is a good example to begin with, though. There's 3 ways I could draw sulfur dioxide. This would be one version. Its resonance structure, then, would be this. So basically the same atom to begin with. The problem with this is my oxygen has a -1 formal charge and my sulfur has a +1 formal charge. Elements that are in the 3rd energy level or lower, which sulfur is in the 3rd energy level, can access d orbitals. So they can make more than 4 bonds or they can disobey the octet rule. And they will do that to avoid formal charge. So another way I could draw this instead, which is the correct way, is to have 2 double bonds. So this is actually the correct version of sulfur dioxide. Because yes, sulfur disobeys the octet rule, 2, 4, 6, 8, 10. But at the same time, the oxygens are still at the octet, there is no formal charge, so this is the most stable configuration for that. Again, next chapter we'll go over the shape of everything like this. The last slide we have for this chapter is on what's called bond enthalpy. Bond enthalpy, different than all the other enthalpies in thermodynamics we went over where it's products minus reactants. This is actually the bond enthalpy of the reactants minus the products. And you have to remember to take into account how many there are. I'm going to do one question on the board, and that's going to be it for this lecture, where we're going to talk about the creation of water from its elements. So, we have to write the reaction of H2 plus O2 making H2O. First thing we have to do is balance this equation. I put a 2 in front of my H2 and a 2 in front of my H2O. Now I make sure to draw Lewis dots for each thing as well so I can tell what type of bonds exist. It is a single bond hydrogen-hydrogen here. It is a double bond oxygen-oxygen here. And there are 2 OH bonds for every 1 water. So how I'd set this up then, of reactants minus products, let's start with the fact that I have 2 HH bonds. I'm going to take 2 times the value given to me, 436.4. These are in kilojoules per mole. I'm going to add to that 1 OO bond of 498.7. These are all my reactants. I'm going to subtract my products. If you look at my product, there's a coefficient of 2 in front of it, but also there's 2 OH bonds. So I have a total of 4 OH bonds. Each water has 2, but there's 2 waters. So if I take 4 times the 460 kilojoules per mole, this minus this will give me my final answer in this case of negative 468.5 kilojoules per mole. Just like in thermodynamics that we went over in an earlier chapter, a negative value means it's exothermic, a positive value would mean it's endothermic. And that is